For years, deploying AI meant querying a massive centralized server. You send a prompt, it sends a response. But production environments demand a different approach. The industry is moving away from the reactive chat interface. Instead, engineers are designing systems where multiple, specialized agents run continuously in the background, anticipating needs rather than waiting for commands. To understand how this operates in practice, we can look at Hermes, a completely sovereign, self-hosted, multi-agent workspace. This interface shows the top-level orchestration layer of the Hermes system. What you are looking at is a live, running environment of discrete agents interacting with one another. These individual nodes, Sage, Ovid, Echo, and Pixel, function as dedicated autonomous blocks assigned to specific system tasks. Modern AI architecture requires building an ecosystem. It is an engineering problem where models are integrated directly with host infrastructure to execute continuous logic. The sheer volume of this background activity becomes apparent when we look at the system telemetry. Over 17 million tokens processed across more than 100 sessions. Driving this intense continuous logic is a local instance of the 35 billion parameter Qwen model. Running a 35 billion parameter model for orchestration presents a strict hardware constraint. It requires a massive amount of VRAM, which typically forces organizations to rent expensive, high-tier cloud instances. That cloud dependency assumes an infinite enterprise budget. For independent developers, DevOps engineers, or any self-hosted environment, computing resources are strictly finite. Hermes bypasses this limitation. It deploys an asymmetric local GPU topology to handle all persistent background reasoning and dynamically routes only the most demanding tasks to cloud APIs. By deconstructing the layers of this specific system, we uncover a replicable blueprint. It demonstrates exactly how to build high-capability AI clusters while operating under strict local hardware constraints. We start at the foundation, the Linux environment running the raw hardware. This terminal reveals the bare metal configuration, an RTX 3060 Ti alongside an RTX 4090. This creates a deliberate asymmetry, an 8GB and a 24GB card, totaling 32 GB of VRAM. Here, Llama Server actively splits the 35 billion parameter model's layers across both cards simultaneously. The lower, compute-heavy layers are routed to the large 24GB block, while the final layers process on the smaller 8GB card. Keeping the Qwen reasoning engine local is an economic necessity. It generates thousands of hidden, background analytical thoughts continuously, incurring zero API costs. This asynchronous pooling of consumer hardware forms the base layer. Without it, continuous sovereign AI becomes financially impossible. With the hardware stabilized, the next layer dictates how this local reasoning engine interacts with external data without requiring human prompts. This jobs dashboard shows the integration of standard Linux cron scheduling directly into the AI workflow. These cron jobs do not simply ping a generic text box. They wake up specialized, system-defined agent profiles, each equipped with specific operational instructions. When the SolarMan cron job triggers, the assigned agent executes raw Python code to pull telemetry from an external IoT sensor API. Here in the live execution, the agent autonomously runs bash scripts. The raw output is chaotic, but the local Qwen model intercepts and parses it. Finally, the synthesized data, a precise 3,834-watt reading from the solar sensor, is formatted and delivered as a direct message. Merging standard Linux utilities with specialized agent profiles turns Hermes into an active, persistent operating system driven by background logic. The 32GB local VRAM pool handles text reasoning perfectly. However, it will immediately fail if subjected to heavy multimodal or high-resolution image generation workloads. The architecture must account for tasks that exceed the physical capacity of the local hardware. When a request demands a complex visual asset, the system successfully returns a high-fidelity image right to the local interface. This happens because the orchestrator detects the specialized request, recognizes the local hardware limit, and temporarily acts as an API gateway to bypass the local Qwen model. The heavy lifting is seamlessly offloaded to external infrastructure. The system routes the prompt to an Azure Foundry instance running the Flux 2 Pro model. You secure enterprise-grade visual output, but you only rent the required cloud compute by the second, exactly when it is requested. All other baseline text, scheduling, and core reasoning operations immediately default back to the free 24/7 local hardware. True system efficiency relies on knowing when to process locally and when to automate seamless off-ramps to external cloud power. Zooming out, we can map the entire resulting pipeline. Everything flows through the central orchestrator, receiving triggers from either user inputs or automated cron jobs. The primary logic loop processes locally, utilizing the 32-gigabyte hardware pool to handle zero-cost text reasoning. When action is required, the system executes scripts within the Linux environment to read external sensors and physical telemetry. Finally, when workloads exceed local bounds, the orchestrator routes specialized requests through the Cloud Escape hatch to Azure. This creates a single, unified pipeline capable of executing highly private, robust physical automation with the ability to scale processing power instantly. The Hermes framework illustrates that deploying one massive model to handle every task is an outdated approach. The future of infrastructure involves precise routing. Engineers must maximize asymmetric, consumer-grade hardware for the persistent logic layer. This protects both operating budgets and proprietary data. Expensive cloud instances are maintained on the periphery, treated strictly as interchangeable tools for transient, heavy-duty tasks. System capability is dictated by environment design. The most effective deployments will come from engineers who focus on building highly resourceful, automated orchestration layers.